Good day everyone, I'm Marisa Rose F. Rodrigo and my partner is Jonna C. Tundag and we are the group 5. So the topic that we are going to discuss is all about permutations and the symmetric groups. So I am the one who will be going to report about permutations. What is permutations? So permutation, it is an action that rearrange a collection of objects. It is also a finite group. Let's say G whose elements are permutations of a given set and whose group operation is composition of permutations in G. A permutations is a set or a blend of the target. It belongs from a kit where the order or the form of selected aims does value. In a quite simple wording, a permutation is a system of objects in a well-defined order. For convenience, we will usually refer to permutations of positive integers, just like we did when we numbered a rectangle, and etc. There are many ways to represent permutations, but we will start with the notations illustrated by the following examples. So here are some permutations of 4 objects. 1 replaced by 2, 2 replaced by 3, 3 replaced by 4, and 4 replaced by 1. And the next, 1 replaced by 2, 2 replaced by 1, and 3 replaced by 4, and 4 replaced by 3. 1 replaced by 3, 2 replaced by 4, 3 replaced by 1, and 4 replaced by 2. And we can also 2 replaced by 3, and 3 replaced by 2. We considered only functions f, a to a, whose domain is a set A and whose range is in the same set A. To begin with, we note that any two functions f and g from A to A are equal if and only if f of x is equal to g of x for every element x in A. By a permutations of a set A, we mean a bijective functions from A to A. That is a one-to-one correspondence between A and itself. In elementary algebra, we learn to think of a permutations as a rearrangement of the element of a set. Thus, for the set 1, 2, 3, 4, 5, we may consider that the rearrangement which changes 1, 2, 3, 4, 5 to 3, 2, 1, 5, 4. This arrangement may be identified with the function. The concept of permutations relates to the act of rearranging every member of a set into a sequence or order, or rearranging each the members of the set if the set is already ordered. Formula: the number of permutations of n items selected are at the same time. Its mathematical term will be like this pattern. P of n times r is equals to n factorial over n minus r factorial. A sign has 4 figures in a definite form, and the numerals are among 0 to 9. So here are examples of this report on permutations. So question number 1. In a sports reporting firm, the supervisor must choose the top 3 aims of the month from 10 shortlisted ambitions. So here you have to find the total number of months by which you can select the fittest and top-notch 3 intentions. So the supervisor has picked the 3 aims of the months that are only 3. After that, the perfect or definite order of the list of ambitions is quite vital. Now, solve the permutation problems. Choose 3 core aims out of 10. So our possible permutations is 10 and 3. Now we can use our formula, which is P of nr is equals to n factorial over n minus r factorial. Rn is equals to 10, Rr is equals to 3. So we have 10 factorial over 10 minus 3 factorial. So we get the answer of 720. Hence, there are 720 steps in choosing the uppermost 3 aims. So here are the types of permutations. First, permutations of n different objects when repetition is not allowed. Second, repetition, when repetition is allowed. And the last one, permutations of multiset, when the objects are not distinct. And also, here is the three groups of permutation. First, the alternating groups. Second, the dihedral groups. And the last, symmetric groups of three-dimensional figures. The next reporter will be Miss Jonafi C. Tondag.
Good morning, sir. Good morning, classmates. My task is to discuss the symmetric groups. So let's start. What is symmetric groups? Symmetry or symmetric comes from the Greek word symmetria, which means measure together. So symmetric group, it is the group consisting of all permutations of the set. Example given, all bijections from the set to itself with function composition as the group operation. It is denoted by S sub n. Definition. Let f be a set of points in real numbers to the power of n. The symmetric group of f in R to the power of n is the set of all isometries of R to the power of n that carry f onto itself. The group operation is function composition. Symmetry group example. Consider the line segment I in real numbers from A is equal to 0 to B is equal to 1. There are two isometries which map I onto itself. F sub 0 x is equal to x and f sub 1 x is equal to 1 minus x. The illustration shown below the example. So the multiplication table for the symmetric group with elements f sub 0 and f sub 1 looks like this. Symmetric group example 1.b. In this, there are four isometries which map I onto itself. First, f sub 0 xy is equal to xy, the identity. Next, f sub 1 xy is equal to 1 minus x and y, the reflection about the line x is equal to 1/2. Third, f sub 2 xy is equal to x and negative y, the reflection about the line y equal to 0. And f sub 3 xy is equal to 1 minus x and negative y, a combination of f sub 1 and f sub 2. The illustration shown first is for f sub 0 or the identity, while for f sub 1 or the reflection about x is equal to 1/2 looks like this. And this one is for f sub 2 or the reflection about y is equal to 0. And f sub 3 or the reflection about x is equal to 1/2 and y is equal to 0 illustrates like this. The multiplication table for this group is given in the right side here. The group is denoted dihedral sub 2 and the composition. There are three figures shown here, and we determine the permutations of each figure, the triangle figure. For rho, these are the following. Rho sub 0 is equal to 1, 2, 3, 1, 2, 3, while rho sub 1, there's changes occur, 1, 2, 3 and becomes 2, 3, 1. And for rho sub 3, 1, 2, 3, 3, 2, 1. And for mu sub 1 as 1, 2, 3, 1, 3, 2. Mu sub 2, 1, 2, 3, 3, 2, 1. And mu sub 3, 1, 2, 3, 2, 1, 3. Using this figure, the mu sub 1, we multiplied it with row sub 1. 1, 2, 3, 2, 3, 1 times 1, 2, 3, 1, 3, 2. And the result is 1, 2, 3, 2, 1, 3. This is the mu sub 3. And this one, using row sub 1, we multiplied it to mu sub 1. 1, 2, 3, 1, 3, 2, 1, 2, 3, 2, 3, 1. It becomes 1, 2, 3, 3, 2, 1. It is the mu sub 2. Using those figures, we find that the multiplication table for the group of symmetries of an equilateral triangle is look like this. This group of symmetries is called the dihedral group, or denoted as D sub 3. Notice that it contains a subgroup, or the order 3. So this time, let's define the dihedral groups. The symmetries of a regular n-gon form the dihedral group, D sub n, and the composition, which consists of 2 times n permutations. These groups are generated by the two fundamental permutations, the rotations and reflections. The next one is cyclic groups. If we consider the symmetries of a regular n-gon, which only consists of the rotations and not the reflections, then we get a subgroup of the dihedral group D sub n, which consists of the n rotational permutations. This group of n rotational permutations forms the cyclic group of order n. The cyclic group of order n is the same as isomorphic to the integers modulo n, or the set of integers modulo n, and so on. Since for each n, the cyclic group of order n is a subgroup of the dihedral group of order 2 times n, we often drop the binary operation and write this as Z sub n less than D sub n. It is an example for cyclic groups. Using this figure, we determine permutations by row. Row sub 0 is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, while row sub 1 is 1, 2, 3, 4, 5, 6, and 2, 3, 4, 5, 6, 1, while row sub 2, 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 1, 2. For row sub 3, 1, 2, 3, 4, 5, 6, 4, 5, 6, 1, 2, 3. And for row sub 4, it becomes 1, 2, 3, 4, 5, 6, and 5, 6, 1, 2, 3, 4. While row sub 5, it becomes 1, 2, 3, 4, 5, 6, and 6, 1, 2, 3, 4, 5. This group of 6 permutations is what we call isomorphic to the group, the set of integers modulo 6, and so on. Let's have generators of a group. The cyclic group Z sub n can be generated by the elementary rotation rho sub 1. That is, each element of Z sub n is a power of rho sub 1. P sub 2 is equal to P sub 1 times P sub 1. While P sub 3 is equal to P sub 1 times P sub 1 times P sub 1, and etc. In fact, the formal definition of a cyclic group is a group which is generated by a single element. So the dihedral group D sub n can be generated by two symmetries, a rotation and a reflection. This is the reason these groups are called dihedral groups. And also the finite symmetry groups. A group is finite if the set G has a finite number of elements. The theorem is the only finite symmetric groups of a set of points in real numbers squared, that is, the only plane symmetric groups or groups of isometries of the plane are the groups Z sub n and D sub n for some n only. These groups are sometimes called Rosette groups. So let's have another example. Let us take a look at S sub 3. First, list all the permutations of the set 1, 2, 3. The epsilon is 1, 2, 3, 1, 2, 3. While alpha 1, 2, 3, 1, 3, 2. And for the beta 1, 2, 3, 3, 1, 2. While the gamma 1, 2, 3, 2, 1, 3. And for the delta 1, 2, 3, 2, 3, 1. And for the kappa 1, 2, 3, 3, 2, 1. For example, we have beta is equal to 1, 2, 3, 3, 1, 2. It is the function such that beta 1 is equal to 3, beta 2 is equal to 1, beta 3 is equal to 2. A more graphic way of representing the same function would be like this. The operation on elements of S sub 3 is composition. To find alpha composition of B, we note that A alpha composition B sub 1 is equal to alpha times beta sub 1 is equal to alpha sub 3 is equal to 2. Alpha composition B sub 2 is equal to alpha times B sub 2 is equal to alpha sub 1 is equal to 1. Alpha composition beta sub 3 is alpha times beta sub 3 is equal to alpha sub 2 is 3. Thus, A composition B is equal to 1, 2, 3, 2, 1, 3, which is the value for gamma. Note that in alpha composition beta, beta is applied first and alpha next. A graphic way of representing this is shown below. Other combinations of elements of S sub 3 may be computed in the same fashion. So the student should check the following table, which is the table of the group S sub 3, shown below. It is difficult to overestimate the importance of symmetry in many aspects of mathematics. On the other hand, symmetries and their groups arise everywhere, not only in mathematics itself, but in nature too. In quantum physics, flower petals, cell division, the work habits of bees in the hive, snowflakes, music, and Romanesque cathedrals. Therefore, symmetry is common phenomenon in the world around us. So that's the end of my discussion. Thank you for listening attentively. And let's have a short exercises.